This is the first part of problem number 37 from chapter 10. There are two circuits here, so we're just going to do the analysis they ask for this first circuit. So the two things that we really need to find is the current through each resistor in part A. This is part A, and then the power dissipated or consumed by each circuit. And then the power supplied. And the power supplied is going to be the power dissipated. So if we can just find the power from the battery, then that answers questions both C and D here. Okay, so we're going to take a look at this circuit. And the first thing to notice about this circuit is that the resistors aren't in parallel or in series. So we've got to use Kirchhoff's laws. Okay, so Kirchhoff's laws say that Kirchhoff says that current in equals current out, and the change in voltage if we go around a loop is equal to 0 around our loop. So these are going to be the two sort of guiding principles for what we do for this problem. So we need to label some currents. And so to try to be consistent with the way the book is going to end up labeling these currents, I'm going to try to label them as they go through the resistors. So we'll have current 1 through resistor 1, current 2 through resistor 2, and current 3 through resistor 3. You can pick any direction you want, but you kind of want to pick the direction that's going to make sense here. And so I tend to look at this as if the battery is providing current. In other words, it's sending current out. If we have current going the other way to the battery, then that's a battery that's being charged up. So this current that's coming out of the battery would also be into, right? Kirchhoff's law says current in equals current out. So this is now going to be the current that's going through resistor 2. So I'm going to call this I2. Same thing here. I would expect the current coming out of this battery to be going that way. So that would be coming this way. And so that is going to be what we call current I3. So I3 looks like this. So I3 is coming along like this. I2 is coming along like this. If they're both providing current in that direction, then I would say this current that meets at this junction would add together and give me a current that would be going down, right? Because all of those currents are going in. So I'm going to call this I1. And so my first Kirchhoff's rule is going to tell me that the current I1 is going out, and that's got to be equal to the two currents coming in, which would be I2 plus I3. Looking at this junction right up here that I've got a red dot. So this red dot junction gives me this equation. And that's my first equation to work with. And I've got to know the current, so that's current 1, 2, and 3. And so I need 3 equations because I have 3 unknowns. And so I'm going to now do a loop, and I'm going to add up the voltages around the loop. So I'm going to start in this bottom corner here, and I'm going to loop around like this. Okay, so I'm going to get rid of some of my current markers because I don't need quite all of them. Okay, there. So if I do this first loop, here, I'll highlight it. There we go. We're going to start at this bottom left corner where the blue dot is there, and I'm going to say this is loop 1. So this is loop 1, or I guess I'll call it loop A because I got too many numbers already. So this is loop A. And the voltage, as I add them all up, the sum of the voltages around loop A is going to equal 0. So I'm going to start at the bottom. I go through the battery in the direction that the battery provides current and provides power. So I'm going to say that's positive V1. Then plus my next thing, I don't have anything on this top. I keep going. I'm going to go through R1, but it's in the direction that we lose potential energy because we're going through the resistor in that same direction. So I would have a minus I1 R1. And then I keep going, and it looks like I'm going through my R2 resistance 2 in the direction that I would also expect to lose potential energy. So this is my equation through the loop. And so this is equation number 2. Okay, we'll put in the values in a minute, but this gives us at least a starting place. Okay, then I have a choice. I can do the outside loop or I can do the inside loop, and I can go clockwise or counterclockwise. It doesn't matter as long as I'm consistent. And so I'll go ahead and do the outer loop so you can see how that goes, but again, it doesn't matter. So this is going to be loop B. Okay, so that's loop B. So we're going to have loop B. And again, we're going to say the sum of the voltages all the way around the loop give me 0. So as I go through this loop, again, I have a plus V1 because I'm going through the battery in the direction that is increasing the power. But now when I get to my second battery, I'm going the other direction. So I need to say minus V2. And then I'm going across this resistor, R3. As I look at this, I'm going against the current. So that means I would have a positive I3, R3. Remember our sign conventions. So our sign conventions, just to remind you, are that if we go through the battery in the direction that it goes, that would be a plus voltage. And if we go through a resistor, if we've got current going that way, if we go through, then that would be a minus I times R, going through the current that way. So if we switch, so this is our sign conventions here. Conventions. So if we're going the other way through this resistor, then going backwards, I get a plus instead of a minus. So that's I1, R3, and then finally I've got this last resistor. Again, I'm going in the same direction that I had before, minus I2, R2 is equal to 0. This is equation 3. Okay, so I have 3 equations and I have 3 unknowns, although it's not obvious I have 3 unknowns. So I'm going to put some numbers in here just so I can keep track of what's going on. So V1, I've got 1.6 volts minus I1 R1, which is 2 kiloohms, minus I2 times 1 kiloohm is equal to 0. So that's my new equation 2. So this is equation 2. Okay, for loop B, equation 3, V1 is 1.6 volts minus 1.4 volts plus I3 times 1 kiloohm minus I2 times 1 kiloohm is equal to 0. So this is my new third equation. So I have 3 equations and 3 unknowns. My unknowns are current 1, 2, and 3. And so my first equation is equation 1, 2, and 3. And so what I'm going to do is I'm looking at my equation 1. And my approach to this, although there are lots of approaches to this, is I want to substitute into equation 1 and be left with one of the currents. And so I look at what current is showing up in all of my expressions. And it looks like I've got an I2 here and an I2. So what I'm going to do is I want to keep the I2. I'm going to write everything in terms of my I2s. So since I have an I2 in every equation, and this one has an I2, what I want to do is replace this with an equation that has I2, which is going to come out of equation 2. So what I'm going to do is I'm going to rewrite equation 2. I'm going to solve for I1 so I can substitute that into equation 1. So I'm solving for I1 on this equation. So I want I1 by itself. So I'm going to take the I1 term over to the other side. So I've got 1.6 volts minus I2 1 kiloohm. I'm going to drop my units, but I'm going to keep my K's there. is equal to, now I'm adding this to both sides, so I'm going to have I1 2K. Okay? Sorry, 1K. I1 times 2K. And then I divide both sides by this 2K. And that gives me an equation for I1. So I1 is equal to 1.6 minus I2 1K over 2K. Okay, so that's an expression for I1 that I can substitute into equation 1. I'm going to do the same thing down here. I'm going to solve for I3. That way I can substitute everything in. So again, I want I3 by itself. So I'm going to take it over to the other side. So this gives me, this is 0.2 volts minus I2 times 1K, somehow I forgot to write that down, is equal to minus I3 1K. Okay, again, I can divide through by 1K, by negative 1K, actually, minus 1K, minus 1K, to get me an expression that says I3, because the I3 will be by itself now, is equal to 0.2 volts minus I2 1K, all divided by minus 1K. Okay, so I've got an equation for I3. I've got an equation for I1. I'm going to substitute, so I'm going to substitute into equation 1. Notice this is all just algebra from here on out. That physics is actually in writing these three equations and getting the signs right to make sure we're actually doing energy conservation and charge conservation. But then after that, it's just algebra. So substituting things in, I'm going to put this expression for I1 into this equation. So I get now 1.6 minus I2 1K over 2K is equal to I2 plus 0.2 volts minus I2 1K divided by a minus 1K. I'm going to go ahead and bring that minus sign up. Okay, so this isn't too bad. You can decide you don't want anything in the denominator, so you multiply both sides by 2K if you want, or you can go ahead and realize that when you have something like A plus B over C, that's the same as A over C plus B over C. And that's true. Notice you can't do the reverse. You can't say C over A plus B. That doesn't work, okay? So, but this works. So you can do this any way you want. I'll multiply probably, well, I'll go ahead and work it the normal way, which would be dividing things out. So 1.6 divided by 2 kilo, this is volts, and this would be kilo ohms, right? I'll go ahead and keep my units in here. Tells me that 1.6 divided by 2, that would be 0.8, and then since I'm dividing by kilo, that's milliamps, minus now I2 times a 1/2, right? Because the kilo ohms cancel out on the second term. So I've divided this into that term and then this into that term. Is equal to I2 plus, let's see, we've got a minus 0.2 milliamps plus an I2. Okay, so now we just collect our terms. And so we've got two I2s. I'm going to add 0.02 milliamps to both sides, right? Plus 0.02 milliamps. I want the I2s by themselves, plus 0.02 milliamps. And then I'm going to add 1/2 I2 to both sides. Plus 1/2 I2. So those go away, and I get 1 milliamp is equal to, let's see, I've got 1 plus 1/2, 2.5 I2, and then that tells me that I2 is equal to 0.4 milliamps. Okay, now we're basically done. We just plug things back into the equations. So I can take this current, this I2, and I can plug it back into our equations for I1 and I3 over here that are boxed. So if I look at this, I plug in 0.4 milliamps here. Then milliamps times K just gives me 0.4. So this gives me 1.2 volts all over 2 kiloohms. So that would be 0.6 milliamps. And then right here, I've got 0.2 volts minus 0.4 milliamps times kilo, so that's 0.4, all over minus 1 kiloohms, so that gives me 0.2 milliamps. If I had picked the wrong direction for the current, like I had guessed I3 was going to the left and it should be going to the right on the bottom, then I would get a negative value down here instead of the positive value, right? Because I have minus 1.02 divided by the minus 1. So it would fix itself. If you guess the direction of the current wrong, you can fix everything up. So I get I2 is equal to 0.4 milliamps, I1 is 0.6 milliamps, and I3 is 0.2 milliamps, and we can check, in fact, we kind of have to zoom in, that I need I1 to equal the sum of the other two, so that works. And then if I want the power is going to be the current coming out of the battery times the battery. So for battery 1, that's V1 and I2. So this is where our labels aren't great. V1 and I2. So that would be 0.4 milliamps. And voltage 1 is 1.6 volts. And so that gives me a 0.64 milliwatts. And then power for the second battery is V2, and the current going through that is I3. So I3 is 0.2 milliamps right here. And the battery is 1.4 volts, so that's a 0.28. I forgot to do my math. 0.92 milliwatts. Not a lot of power, but that's because we have small batteries and fairly sizable resistors. So we're not drawing a lot of power from these batteries. So the point of all of this is that you can make the analysis. The important part is really this current in equals current out, Kirchhoff's, and the sum of the voltage around the loops is 0, assuming we're using the right sign convention so that we can take into account the increase in potential energy as provided by the battery, the increase in electrostatic potential voltage, and then the decrease as we come across a resistor in the direction that current flows. And then after that, it's just setting up the equations and solving for it.